there's an interesting result in this section, and that's that the acceleration always lies in the Tn plane. Now, in 2 space, that's not remarkable at all, because in 2 space is the xy plane. All planes in 2 space are the xy plane. Okay? But in 3 space, where we've got the TNB system, the unit tangent, the unit normal, and the unit binormal vector, this says the acceleration always lies in the plane determined by t and by n. And we can actually demonstrate that it will lie in the plane if it's a combination of some t's plus some n's. We call that a linear combination anytime you have some of these plus some of those. So if I can write acceleration as a sum of some t's plus some n's, that will demonstrate that it lies in the Tn plane. And I can do that. So let's suppose that r of t is my position function in 3 space, because again, this isn't very remarkable in 2 space. So then we'll say that r prime of t is our v of t is our velocity. And of course, we know that the magnitude of r prime of t is the speed. I'm going to here use the convention that is often used in physics classes, and it's not universally used in this textbook, but it is used for this particular example, that I'm going to just call that v without the bar over it. So very often in physics, when you have a vector function, if you write the name of that function but without the bar, they use that to mean the magnitude of the function. I'm not using that convention universally in this class, so anytime you do use that convention, make sure you tell me. Just like I'm telling you right here that for this problem I'm going to use that convention. Just make sure you identify that. Notice if you do use that, it becomes super, super important that you don't leave off the bar when you're talking about the vector function. All right. Now, with this, I'm going to express my velocity function as a product of a scalar function and a vector function. I know that anytime I have a vector, it has a magnitude and a direction. So if I represent that direction with a unit vector and then just scale it by the correct magnitude, that gives me the vector that I want. Well, for velocity, I know that's just r prime of t, but I know the unit vector that points in that direction, it's just going to be the unit tangent vector. Now, I'm not saying these are equal yet. I've still got to fill in the scalar function that I'm going to scale this by, okay? But that's the unit vector that gives me the direction that I just have to scale by the magnitude. Well, the magnitude is the speed, which I've decided to call v. Now, I am going to write that that's v of t, because it's not a constant, it's a function of t. It's just a scalar valued function of t, by which I'm scaling that unit tangent vector. Okay. Now, if I write it this way, then if I look at my acceleration, which I'm going to write as a of t, I know that's v prime of t, but that just means I'm taking the derivative of this product, v of t times t of t. And we have a product rule for this sort of product, where I have a scalar function that I'm using to scale a vector function. So I'm going to get v prime of t, the derivative of speed, times t of t, plus v of t, the speed, times t prime of t. Now right there, I've built the acceleration as a sum of some t's and some t primes. But I know that t prime is parallel to n, because n is just t prime normalized. If it doesn't make sense to talk about the Tn plane if n doesn't exist. So if t prime was 0, then n doesn't exist. But in the cases where the Tn plane actually does exist, because there is a unit normal vector, I probably should have stated that at the beginning. Okay, so from here, I can actually see that this puts us in the Tn plane, because this is just going to be a multiple of n. I can actually take it a step further. I can get it to the point where I can see I've got some t's and some n's. To do that, I'm going to use the fact that curvature, kappa of t, is the magnitude of t prime of t over the magnitude of r prime of t. Now, that's not a formula I have memorized. That's a formula I looked up in my notes before I started shooting this video. And I'll even confess, this is take 2 because I forgot the formula. And sometimes when I forget something, I can very quickly look it up, but I just totally botched the first take of the video. So, we're on take 2. Okay, so I don't have a double standard. I'm not expecting you to have that memorized. You should know this fact, that acceleration lies in the Tn plane. You should certainly be able to write the velocity as this product of speed times the unit tangent vector and take the derivative, but I'm not expecting you to have that formula memorized. Okay, so this step where we're going to take things a step further in order to get this as some t's plus some n's, and I'm basically trying to figure out how many n's I have, not responsible for doing unless the formulas are provided for you. Okay, but this allows me basically to solve for the magnitude of t prime of t. So the magnitude of t prime of t is just kappa of t times the magnitude of r prime of t. I'm going to just abbreviate that as kappa, remembering that that is a function of time, and this is my speed, kappa times v. Well, if that's the magnitude of t prime, then I can say that t prime of t is actually just kappa v times n of t. N of t would be the unit normal vector. That's t prime normalized. So this is the unit vector that points in the direction of t prime. This is the magnitude. Once again, I'm just scaling that unit vector by its magnitude. But then if I plug that in here, I can say, okay, we've got v prime of t times t of t, plus there's a v, actually, looks like I'm dropping the t, so I'm just going to call that v prime, which I know is a function of t, times t. Let's just drop all of that. Plus, I'm going to have v, the speed, times kappa of v times n. So I'm going to have kappa v squared times n. Okay. All right, so the acceleration is v prime t plus kappa v squared n. Not a formula you need to have memorized. You should know the result that it is in the Tn plane, so that it's some t's and some n's, but I don't expect you to have the formulas memorized for what these scalars are. This is sometimes written as a sub t. That's the tangential component of acceleration. And this is sometimes called a sub n, which, as you might guess, is the normal component of acceleration. Okay, so again, I'm not concerned that you have that result memorized, except that you know that acceleration lies in the Tn plane, but it was an excellent opportunity to review how useful it can be to sometimes express a vector by scaling the unit vector that gives us the direction by the correct magnitude. All right, that wraps up what we are officially covering for this section. I think I mentioned it was a short section. I did not lie. Now, there is one other topic that's really cool that's covered in this section, and that is Kepler's laws. Okay. I am not officially covering Kepler's laws in the interests of time. That's because it really is a standalone topic, and we've got the skills at this point to, with a few basic simplifying assumptions, which people always make when they're trying to model the real world situations, with a few basic simplifying assumptions, we can actually derive Kepler's laws. The most interesting of those is that the planets orbit the sun in an elliptical path. This is me being a planet orbiting the sun in an elliptical path, in case you didn't know. Okay, that's a really cool result. It's not particularly intuitive or obvious. It's fun to work through, I think. It's a puzzle. But it's not the sort of thing that I could hold you responsible for, and it is the sort of thing that is time consuming to take a look at. So here's what I've done. Okay, there is a video series, there's a playlist on Kepler's laws. It's entirely optional. Usually what I do when I'm teaching in person is I poll the class, and if there's enough interest, we find a time outside of class and I just deliver the lecture on Kepler's laws. And people come if they're interested and people don't come if they're not, and no consequences either way. Okay. Obviously we can't do that, so I've got the video lectures. So if you are interested in that, you're more than welcome to watch that. I should let you know, I created those based on the argument proving Kepler's laws from the book by Anton Bivens and Davis. That's the textbook that we used to use. We're currently using Stewart. Kepler's laws haven't changed, but Stewart takes a slightly different approach and uses a slightly different proof. So if you do watch the videos, don't use your textbook to try to clarify the argument, because it's a different argument for the same thing. Okay? So if you're interested, watch the videos, enjoy them. I'm certainly happy to answer questions about them, but you will sort of see it's not particularly intuitive. I think one of the things that's very interesting is it gives you a little bit of sense of how math sometimes actually gets done. Okay? When you're doing your math problems, I teach you a skill, and then I assign problems from the section of the book where that skill was covered. So you're always given a problem to do that deals with the skills that you were just taught. Now, some of that does involve some problem solving and some racking your brains and stuff to figure out how to use the various tools that we've done. It's not just mimicking. But with Kepler's laws, it's kind of crazy. Very often what happens when you're trying to prove math is you just write down a bunch of things that are true, and most of them are not at all useful. Okay? And then you look at things and you say, oh, that one there and that one there, maybe I could put those together and that would be useful. And you get to see that a little bit in the derivation of Kepler's laws. So if you're interested, you're welcome to watch that, but this is all you're responsible for in section, what is this, 13.6.